Okay, this is our last guest lecture with proofing. So please open your video or your camera and then listen carefully and prepare your questions to discuss this afternoon. To shorten the time for Mr. Proofing, this time is yours, please.
Welcome, everybody. I hope you can hear me. Everybody can hear me, I hope. So yes, we're gonna continue where we stopped yesterday. And if you remember, yesterday we talked about, hold on, I have to. So if you remember yesterday, we talked about general concepts in hydrogeology. I talked about porosity. I said that porosity is a measure for how much water a given quantity of a geologic material can hold. I explained the difference between porosity and specific yield. The specific yield is the amount of water that drains out of this porous material, and then a certain amount is being retained, which we call the specific retention. We also defined what is groundwater in the first place, and we said that any water held in pores or in fractures or in fractured geological materials like rocks and sediment is called groundwater. And the geologic formation that both has a high porosity and a high permeability, we call it an aquifer. And in terms of aquifers, we said there is an unconfined type of aquifer and a confined type of aquifer. The difference is the unconfined one is open to the atmosphere and can be directly recharged from the surface, whereas the confined aquifer is covered by a layer that is not permeable and through which water cannot migrate. The water level in a well in a confined aquifer we called a piezometric surface versus water table in an unconfined aquifer. These are important differences because in a confined aquifer you can have water under immense pressure and possibly even flowing out at the surface like in an artesian well. In an unconfined aquifer, the water table will only rise to the level where the hydraulic pressure is equal to the atmospheric pressure. We then went ahead and talked about what is the hydraulic head. The hydraulic head, if you remember, is basically an energy level that describes how much energy a given amount of water has at any elevation. We used that concept, the Bernoulli equation, to describe how flow of water is being initiated and based on physical terms. And then at the end of the lecture, we talked about Darcys Law. And Darcys Law, if you remember, states that the flow of water, Q, is equal to the cross-sectional area, A, through which the flow takes place, and the hydraulic gradient, which is the ratio of the change in head over the change in length. So this part of Darcys Law is called the hydraulic gradient. And then most important, you see the K. The K is the hydraulic conductivity. It is a measure for the how easy it is for the aquifer material to conduct water. A high K means the material has a high conductivity, easy for groundwater to flow through. Low K means that's the opposite. So it's very difficult for water to flow through material with low K. Okay, moving forward, oops, how do I do this again? Okay, so today we want to talk about how we actually can measure these important parameters like K, hydraulic conductivity. How can we measure the specific yield of an aquifer? Or how can we measure the hydraulic parameters that let us talk to the town manager, for example, about how much water they will get from a well, or talk to the industrial entrepreneur that needs so much water for his industries. They want to know how much water can be pumped from a well, and we need to be able to answer that question. So I will talk about the basic assumptions about what is hydraulic testing. I will tell you what is the cone of depression, how does it look like. We'll talk about radial flow of groundwater to a well. And then we get into how we actually make sense, or how do we quantify these important hydraulic parameters like conductivity and so on, using the Tice method. And then finally, I will tell you a little bit more about how such a test is actually performed in the field. Yesterday, I recommended a textbook that was specific to hydrology. Today, I have another textbook I recommend, and this is called Groundwater and Wells, and it's very specific to hydraulic testing, pump testing, and I would highly recommend it if you can find it. It's a very, very good book that helps you better understand about hydraulic testing. So let's start with a simple question. If you have a well, you probably have a well to pump drinking water or irrigation water, but there are other uses for wells. For example, wells can be used for controlling saltwater intrusion, or wells can be used to remove contaminants from aquifers for remediation. Wells can be used to lower water table for construction purposes, and can also be used to inject fluids into the ground. So wells have many uses, and for us, the most important one here right now is to use wells for conducting a pump test. So what is aquifer testing? In an aquifer test, we have a pumping well, a well from which we pump water, and an observation well. An observation well is basically used to measure the depth to the water table once the pumping well starts pumping. And the information that we're getting from these tests is hydraulic conductivity, K, remember Darcys Law, hydraulic conductivity, K, transmissivity, which is related to hydraulic conductivity by the thickness of the aquifer. So transmissivity, T, is simply the conductivity times how thick the aquifer is. So the thicker the aquifer, the higher the transmissivity. So these two are very important parameters. Another parameter is storativity. That's a parameter you would use in a confined aquifer, or specific yield in case of an unconfined aquifer. So these are our important parameters that we try to get from conducting an aquifer test. Okay, so let's begin with what happens when you start pumping a well. So in this picture here, you see a well, all right? And blue means the area is saturated, that's the saturated zone. And the brown area is the unsaturated zone. Okay, and the dashed line here is the initial water table. So this would have been the water table, or the level in the well where the water was there. Now we start pumping. And when we start pumping, we basically sucking out the water from the porous material. And what happens is we're forming what is called a cone of depression. See this dashed line here? Looks like a funnel, like a V-shaped area. And we call it the cone of depression. This is what forms, or what happens when you start pumping from a well. The water table drops and the cone of depression forms. And we can learn a lot from the shape of this cone. The cone of depression tells us a lot about hydraulic conductivity, transmissivity, storativity, and so on and so on. So what can we learn from the cone of depression, from its shape? It increases in depth and it becomes wider over time. So the longer we pump, the cone of depression becomes deeper and wider. deeper and wider. And we can measure the drawdown, that is the difference between where the level of the initial water table was to where the cone of depression is. This difference, I go back 2 slides. So the drawdown is the difference from where the water table was initially, this dashed line, and where the water table is now. So here's the water table at this point in the well itself. It was initially here, now it is here. So the length of this arrow we call drawdown. It's the amount of water being drawn down due to pumping. So the drawdown is directly proportional to the pumping rate, as we would expect from Darcys Law. The longer and the more you pump, the more drawdown you create. And it's also, the drawdown is inversely proportional to the aquifer's hydraulic parameters. That means the higher the conductivity, the higher the restorativity, the higher the transmissivity, and so on, the lower is the drawdown, or the less is the drawdown. So high drawdown means a lot of pumping, or it could also mean low conductivity, low transmissivity. So the trick now is to make sense out of all this information. And that's where aquifer tests come in. So in an aquifer test, we purposely pumping a well and we measuring the drawdown inside the well and in nearby observation wells. So we have at least one well, that's the pumping well, and ideally we have one or more observation wells, which are relatively close to the pumping well, maybe 10 meters away, maybe 100 meters away, so relatively close. And what we're measuring is time since the test started, and we're measuring the drawdown at any point in time. All right, so we're basically measuring 2 things, time and drawdown. And that's enough to then calculate conductivity, transmissivity, storativity, and so on and so on. So this is the type of data one would get from a aquifer test. Here's the time, minutes, 3, 5, 8, 12, 20, and so on, 500 minutes, right? And at each time, we have a drawdown. At time 0, nothing happens, therefore drawdown is 0. Then after 3 minutes of pumping, the drawdown is already 9 centimeters. After 5 minutes, 21 centimeters. After 90 minutes, 204 centimeters. And at the end of the test, in this case, the drawdown is 332 centimeters. So for each aquifer, these numbers will change. So sometimes the drawdown is a little bit more, a little bit less, but it's related to the aquifer's properties. And that's what we're trying to figure out. So when I take this when I take this data set and plot it, then I have time on the x-axis. Okay, so 0 minutes, 100 minutes, 500 minutes. And on the y-axis, I'm plotting the drawdown. So basically this column here. And drawdown, again, remember, means initial water level, that's H0, minus the water level measured in the well. That's our drawdown. So when I print this data set, what I'm getting is a curve that looks like this, meaning after pumping starts, the drawdown begins to create a cone of depression, and the longer I pump, the more drawdown I'm getting. So this is a very typical data set one would get if one has a pumping test going. And we're going to use this data set a little bit later to evaluate these parameters I was talking about earlier. Okay, so now we have to think about the length of the aquifer test. I can pump forever, theoretically, let's say 1 week, 2 weeks, 3 weeks, and I get a very nice data set, right? I mean, I can pump and pump and pump, and eventually this graph that I showed you here will flatten out. So basically this will become a flat line. we call this steady state, right? So where nothing changes, steady state. And that's possible, takes a long time. But it also is costly because when you run a pumping test, you have to pay for energy, you have to pay for the pump, for the manpower, for renting equipment. So this is a cost, but also it is not necessary. It means we don't have to wait for weeks. We can also use a different type of solution called the Darcys method. The Darcys method, apologies. Darcys method. And I can do the same, but I can run the test much shorter. Let's say 1 day or 12 hours. That would be so much easier because I only have to sample for 12 hours instead of 2 weeks or 3 weeks. So let's focus on short hydraulic tests that we can evaluate with the Darcys method. Okay, so I introduce you to how we change Darcys Law that we talked about yesterday and make it so that we can use it to evaluate our hydraulic test, right? So remember, the flow Q is equal to the hydraulic conductivity times the cross-sectional area times the hydraulic gradient. And remember, there's this minus sign here, which means that water flows from the high to low pressure. Okay, so Darcys Law is what we figured out yesterday. Now, when you start pumping, then the flow towards our well is really radial, meaning the flow comes in from all sides, as indicated in this top view, where water flow is pulled in, the water is pulled in radial fashion to all sides of the well. In plotted as a side view, you can also see in the middle of the well, and then we have our flow lines towards the well, and so on and so on. So why do I bother? Because radial flow requires radial coordinates, meaning we have to rewrite Darcys Law so that it is actually describing what's really going on in the field. Okay, so Darcys Law, I have here now rewritten in radial coordinates. It's still Q, the flow, and it's still K, the hydraulic conductivity, and it's still the hydraulic gradient, dH, dL. What changed is that I'm expressing the area now in radial coordinates. So 2 pi r is the radius of the cone of depression, and B is the thickness of the aquifer. Okay, so this would be the radius r, and B, unfortunately that says H here, but it's I mean B would be the thickness of the aquifer. So it looks very similar to Darcys Law, except now we have the radial coordinates. The next thing I do is I take the K, hydraulic conductivity, and I replace it with T, the transmissivity. Remember, transmissivity is simply the hydraulic conductivity times the thickness of the aquifer. And when I do this and rearrange this formula here, I'm ending up with this formula. And it's still Darcys Law, but it's now written in terms of transmissivity and radial coordinates. And in the next step, and this is where Dr. Theis comes in. Dr. Theis was a scientist who lived about 100 years ago, or died 100 years ago. And he was a very clever hydrogeologist who basically said, okay, if I take this previous equation, Darcys Law, Darcys Law, and rewrite it again slightly different, taking into account the drawdown. Remember, the drawdown is what we measure in the field during the pump test. And then introduce this new term here, which is called the well function. WU is the well function. With this little change, I can now calculate what is the hydraulic conductivity or the transmissivity of the aquifer, how much water it will deliver if it's being pumped, and how much water table drawdown I will observe during pumping. So this WU is an interesting new element. It's called the well function. And it turns out that for every WU, there is a U. So what does that mean? WU is the well function and is basically the well function of any given U. So if I have a U, I can calculate W of U. And U in hydrology is related to the transmissivity of an aquifer and its storativity. See, T, transmissivity, storativity. And that's exactly what we want to know. So if we know U, we can calculate S and T. Okay. So how do we find U? I mean, where is this U and where's this W coming from? And this is the so-called Darcys method, where we can calculate U and WU. All right. And I said for every WU, there is a U. So people using this kind of table, where in this column on the left is any value of U you can imagine. Let's say in this example, let's pick 6.5 10 to the minus 5. 6.5 10 to the minus 5. So we're somewhere here. It's a little bit more than 10 to the 5, a little less than 6 to the 1 to the minus 6. Okay. So this is the line that we have to look at. So next is we have 6.5. So that's between 6 and 7. All right. So 10 to the minus 5, 6, 7. Okay. And 6.5 is basically right in between these two numbers, 9.14 and 8.99. So halfway in between, 9.07. That's our WU. Remember, for every U, there's a WU. So if our U is this, then we take this table and find out where is WU. All right. So every U has a WU. Okay. So let's say we do this for 100 different U values and then take those numbers we got from the previous table and plot them. Plot them in the log graph like shown here. So we have our WU, and for each WU, we have a U. To make it a little bit more complicated, in the Darcys method, we not just take U, we take the inverse of U, so 1 over U. All right. So again, we take our table, calculate WU from U, and then we simply plot that information. And then what you get is a curve that looks like this. That's called the Darcys type curve. And if you think about it, it looks an awful lot like the drawdown data that we have already observed in the field. And I showed you earlier the graph, the drawdown. So interestingly, we can now use this graph to lay over or to superimpose on our drawdown data. And when we do that, then we're in a position to actually calculate all these beautiful parameters that we so desperately need. So remember, this was our data set, time, drawdown. When we print it, it looks something like this, right? Okay, so this is the measured data. And in the next step, I take the Darcys type curve that I just created. That's that line here. I hope you can see the line. And try to match it to my observed data. See, the points are the data, and the solid line is the Darcys type curve. And all I have to do is take these two sheets of paper, the graph on the one paper, the data on the other paper, move them along and find the best matching agreement. And that's not very difficult at all. It's all you need to do is move these two graphs on top of each other until most of the points match the line. And when you have done that, then you have what is called a matching curve. All right, so there's a little bit of graphing and a little bit of overlaying involved, but bottom line is you pick any point, it doesn't really matter, and make this your matching point. That means the data, the corresponding data of drawdown and time as well as the corresponding 1 over U and WU can be extracted from this graph, and then in the next step used to calculate transmissivity and storativity. And that's it. We basically have now calculated our transmissivity and our storativity. And that's really what we wanted to do when we're running a pump test, to calculate the transmissivity and storativity. Okay, that's the bottom line. It's something that is being done every day. This is where hydrologists earn their money. Many young hydrologists go out in the field and run these tests. They're basically spending time in the field measuring drawdown and reporting the time. And then they go back to the office and do exactly what I showed you, plotting the data, matching it with the Darcys type curve, and then calculate the aquifer parameters, transmissivity, storativity, and so on and so on. So this method is called the Darcys method. And the first time around, you probably need some help. Somebody who has done such a test will probably have to teach you. This is the theoretical background. Again, not something you, it's not something very intuitional, but it is very easy to calculate these compounds, these values, once you have seen it or have done it once. Okay. So at this point, you have now the tool to calculate all the important parameters. The tool is the Darcys method, and the pump test or the aquifer test is the field method. So let's talk about how such a test is actually being conducted. So the next slides are all about how to conduct an aquifer test. All right. So remember, I was saying you need a pumping well. Okay, this is our pumping well. To measure the drawdown, here's the cone of depression, right? The cone of depression. Drawdown is the difference between initial water level here and the current level here. So this difference is drawdown, okay? You can measure the drawdown either in the pumping well or in a nearby observation well, or both. You can measure in both. So when you start pumping from the pumping well, the water level will drop. So the drawdown increases. The cone of depression will become larger, meaning that in our observation well, the drawdown is also increasing over time, right? Okay, so time is what we measure, and we're measuring the drawdown. So in the test, then, we pump the well at a specific rate, and then we record in the nearby observation well the drawdown. That's what the pump test is. And most of the time, we take the time drawdown data and then use the Darcys method that I explained to you just a minute ago. Darcys method, right? And with that data, we calculate the aquifer's hydraulic conductivity, transmissivity, and so on and so on. So this is really all it is. It's a set of wells that are being used to measure the drawdown when the pump is running, and the data is being used to calculate the hydraulic parameters of the aquifer. This is all described in this EPA, Environmental Protection Agency document that you can download from the internet for free. All you need to do is type into Google EPA /540/S93 and so on, and you should be getting access to a PDF PowerPoint PDF file that's called Groundwater Issues, Suggested Operating Procedures for Aquifer Pumping Tests. So the following information is part of this document, and again, you can download it for free if you like to learn more about. So a pumping test is not something where you just show up and start pumping from a well. So it requires some homework that needs to be done before you start a test. The homework means, as a hydrogeologist, you first have to think about, where am I conducting this test? What are the geologic characteristics of the area where I'm running the test? Is it sand and gravel aquifer? Is it a bedrock aquifer? How deep is the water table? Is the aquifer a confined aquifer, an unconfined aquifer? How thick is the aquifer? How deep it is? And which direction is groundwater flow, right? I also want to know if there's any wells in the area already, right? Because if I start pumping from one well, but a nearby well already being used for, let's say, irrigation water production, then I need to know about it, because it makes my test a little bit more complicated if I'm not aware of a well being pumped nearby. My data will be invalid. So this is the type of homework I need to do before I go out in the field, before I actually do the test. And some of this information is readily available from maps or from books or from other reports. Some of it may require that you go out in the field first, do some mapping, do some investigations. When all this is done, then you're ready to plan for the aquifer test. And what it is, it's basically something like this. So here's our well, and here's the pump, or I should say the pump is in the well way deep down, but the well is connected now to a pipe, and the pipe is used to pump the water away, right? I mean, so when you start pumping from a well, you want to make sure that the water gets pumped as far away as possible, because otherwise you're going to flood this whole area, and that would not be good in the first place, but it will also change the test outcome. So we call this a wellhead, and here's the pipe that goes away from the wellhead that the groundwater is being pumped away. So again, we don't have X-ray eyes. So this previous slide, look at this part here, is what we're seeing on top of the earth, but below the surface, the well goes way down, right? And the thickness of the aquifer is this length here. So many wells go all the way down to the bottom of the aquifer. We call these wells fully penetrating wells, meaning they penetrate the aquifer fully. And most often that's how you want to do it, because this type of well would give you most groundwater. However, sometimes it is either not possible or too expensive to drill all the way down. And then you end up with what is called a partially penetrating well. A partially penetrating well doesn't go all the way through the bottom of the aquifer. We can still use it for our pumping test, but we need to know that it is a partially penetrating well and not like this one, a fully penetrating well. All right. So ideally, we want a fully penetrating well, but sometimes we only get a partially penetrating well. We can still run a pump test, no big deal. We just need to know what we're talking about. And again, from this previous picture, you wouldn't be able to tell if this is a partially or fully penetrating well. You need to do your homework and figure out first what you're dealing with. Okay, so here's our well pumping, and here are now our observation wells. You can have one, sometimes you have many, like 1, 2, 3, 4, 5 in this case. And each observation well basically measures the drawdown, the depth to the water table at any given time, right? So while doing so, you may also measure rainfall, atmospheric pressure. This is auxiliary information that you may need for making the greatest sense out of the data. But the bottom line is measuring drawdown. And again, this is the cone of depression at different distances from our pumping well. So you have pumping wells, one pumping well and several observation wells, ideally. Okay, but let's say this in the middle here is our test well. And I said earlier, what if somebody next door also has a well and they start pumping their well, or this neighbor? So we have now our well in the middle, and all of a sudden we're noticing that the water level in our well is going down, even so we are not pumping, or it's going down quicker. That means, likely means that somebody in the neighborhood has turned on their well. And what that means for us, they making our test a little bit more complicated, if not impossible, to evaluate. We call this the problem of overlapping cone of depressions. So here's our cone of depression. And as you can see, they overlap. And that's not good news if you want to run a pump test and you have a pumping well or two or more nearby. At least you need to know about it. Ideally, you talk to these people and say, oh, please don't pump for one day while I'm doing my test. Otherwise, I have a problem. Okay. So now we're ready. Let's say we have done our homework. We have our pumping well. We have our observation well. We have talked to the neighbors, asked them not to pump their well. So the next question is, how much shall we pump? How much water do we want to pump? And this is where it gets interesting. It depends how much water you pump, depends on the hydraulic conductivity of the aquifer and the transmissivity. So usually we're pumping at what is a constant rate. That means during the entire 24 hours or how long the test lasts, we're pumping with the same rate. Let's say 1 cubic meter of water per minute. This would be the constant pumping rate for the entire test. Sometimes people like to vary the flow as well. These are called variable flow tests, where instead of using constant pumping rate, over time they're increasing pumping rate. Let's say for the first 12 hours, they're pumping at 1 cubic meters per hour. And then the next 12 hours, they're pumping at 1.5 cubic meters per hour, and so on and so on. What I'm saying is, most people prefer to use constant flow, but variable flow is also possible. So the pumping rate is another decision you have to make as a hydrogeologist. How much water do I want to pump? And then you have to either decide to do it constantly or do it variably. So let's look at this graph for a second. At the bottom is time. Okay, here's the beginning of our test. And then time goes on. So this could be minutes, hours, days. And here's the observed drawdown. So when I start pumping, I see the water level drop, right? So the water level drops. The longer I pump, the more drawdown I get, okay? So remember, this is the original water level. This is what happens over time, okay? So the drawdown continues, go down. All right, so at this point, I decide the test is over. It can be like 24 hours, 48 hours. I decide the test is over. I turn off the pump. What's going to happen? The water level inside the well is coming back up. So here you see the drawdown is going into reverse and the water level is rising. And if I wait long enough, it's again the same as the blue line here. So that's interesting, right? We have drawdown during pumping. When I stop pumping, the water comes right back up. And these curves are actually more or less identical. So identical in the sense, if you flip them, then you will see that they're very similar. And again, the shape of this curve tells us about the hydraulic conductivity and Darcys Law and the parameters. So in our aquifer test, we're doing this part first, pumping, then eventually we're done, we turn off, but then we're not going home. We basically recording also the recovery of our well as it happens when there's no pumping going on. All right. So you end up with a data set that has both drawdown and recovery. So the flow rate is something, like I said, you determine either variable or constant. So how do you measure flow rate? Okay, flow rates are measured with what is a flow meter. And they come in different sizes. This is a fairly big one. You can pump maybe 1,000 liters per second per minute with this type of flow meter, and you can still measure. So bottom line is, when water is flowing, there is a wheel inside here that is turning. Actually, 3 wheels. One is turning slowly, one medium, and one is turning super fast. One is for liters, for single liters. One is for tens of liters. One is for hundreds of liters. And then in this window here, you will see the cubic meters. So in other words, this little apparatus allows me to measure at any given time what is the Q, the flow rate. Remember Q from Darcys Law, that's the flow rate. So we measure the flow, the Q, then we measure the water level. How do we do that? Water level meters look like this. It is basically a sensor, a metal sensor, that when it hits, when you lower it into the well, so this is a wheel that has a lot of tape, this type of tape, you can see it down here, and you put the sensor into the well and then you lower it down, down. And if you look carefully, you can see that the tape has markings. And these markings are in centimeters. So for each marking is 1 centimeter. And then let's say this is 3 meters, and it's 3.20 meters, and so on and so on. So this metal sensor is now going down the well. And when it hits the water, it starts beeping. This thing starts beeping, and you know when the beeping starts, you reach the water table. Then you stop, you not continue lowering, and you take a reading right at this point of what it is. Let's say it says 2 meters 85. That means we are now at 2 meters 85 beneath the surface. All right. And then as the pump test continues, the water level is dropping. You lower the logger a little bit more, and still it starts beeping again. Then you look at your stopwatch and say, okay, 5 minutes later, the next reading is 2.95 meters. So we basically have 10 centimeters difference compared to the first reading. So you do this then every hour for 12 hours, 24 hours, even longer. And you write a report, or basically use a table that looks like this, where you report the time, let's say first hour, second hour, third hour, okay? And then here you'd write down the reading from your water level meter, 2.9, 2. Whatever. The reading is being recorded for each time. And then you look at your flow meter, the flow meter, the blue flow meter, remember this thing here? Okay. You're also reporting the flow meter reading. Okay. And what you get is a really nice data set of time versus drawdown. And this should also be always constant. Then you can have a data set you can evaluate for the various parameters. You also want to write down where is the well, what's the name of the well, right? Locality, how deep is the well, what was the initial water level, right? So all this information you would write down too, because after the test and maybe 6 weeks later, you don't remember where was that well, what was the name of the well. You want to write this down every time you conducting a test, because if you do these tests every day, you will not remember. So it needs to be documented properly. All right. So this is how our data is being generated, the time, the drawdown, and now I can evaluate the test with the TICE method. Okay. I said this is one way to measure water level. a little bit more fancy, we can also do this automatically. And this thing is called a data logger. The data logger is a very fancy device. It is basically a little mini computer that measures temperature, time, and it measures the depth to the water. So you connect this device to a computer, program it that every 5 minutes or every 5 seconds, whatever you like, it is measuring the depth to the water. So instead of doing it by hand, this logger is measuring everything for you. And that's, of course, great, because now you can go to sleep for the 24 hours waiting until the test is over and not sit there next to the well and do these manual readings. Instead, you have this automatic logger do this for you. So these are very interesting, very powerful instruments. However, they're not cheap. In America, they cost about $1,500 per instrument. But they help to cut down personal cost, and also you get much more information instead of doing it by hand, as I showed earlier. Okay, so how often shall you measure? Every second? That seems a little crazy, right? If you measure the water level every second. It turns out that you should measure more often at the beginning of the test than during the later parts of the test, because at the beginning of the test, the water level is dropping very quickly. Later on, the drop is still there, but it's much slower. So initially, you want to test every half a minute. Every half a minute, you take a reading for the first 5 minutes of the test. After 5 minutes, up to 60 minutes, it's okay if you measure every 5 minutes. After 2 hours, after 1 hour and 2 hours, it's perfectly fine if you measure every 20 minutes. And later, after 2 hours, to the end of the test, it's fine if you measure once per hour or every 60 minutes. Okay, so this is just a general guideline. If you're eager, you can certainly measure more often, but you should not measure less than every 5 minutes during the first hour or every 20 minutes during the first 2 hours, and so on and so on. Okay, so now here's your data. Let's say you only have taken 4 measurements, 10 minutes, 60 minutes, 2 hours, 6 hours. And this is the observed drawdown from our water level meter, so 11, 21, 23. And when we plot it, this is the data we get, right? It's like we have seen before. The longer you wait, the more drawdown you get. So this is the raw data, which now allows us to use the Darcys method to calculate our aquifer parameters. Oh, I wanted to show you this picture. This is a picture showing where that water is going from the well, right? Remember, the well had a pipe attached, and often what hydrologists do is they pump the water into a nearby lake or into a nearby river, and that makes that ensures that their site is not going to get flooded. Okay. So the test duration, like I said, is anywhere from 12 hours to 48 hours, depending on your budget, depending on the aquifer characteristics. Sometimes it's necessary to have longer tests. That is particularly true in unconfined aquifers, right? Sometimes you're not allowed to run a test longer than, let's say, 24 hours because the neighbors want to turn their wells back on. So sometimes you have limitations. So this graph or this table shows you roughly for how long or what minimum pumping times look like. So let's say in a fine sand material, you want to pump 30 hours. In a medium sand coarse material, a 4-hour pump test may be okay. But if your material is silt and clay, you may have to pump much longer than that. 170 hours, that's almost, was that like 5 days at least. So it really depends on the material, and that determines the length of the pump test. Okay, so a pump test is the tool, the main tool of an hydrologist, and it's probably the most powerful tool we have to determine aquifer characteristics. However, they relatively complicated, not complicated, but complex, because you need to install a pump, you need to have a pipe to discharge the water, you have to have observation wells, you have manpower to collect the data. So these tests can be fairly expensive. So sometimes if there's no budget or very limited budget, hydrologists use a little trick. So instead of pumping water from the well, they're adding water to the well. They're basically taking a big barrel of water and dump it down into the well. That's crazy, right? Why would they do that? Think about it. So you dump water into the well, the water table comes up inside the well, right? And then slowly the water inside the well will drop. The water table will drop because the additional water is now flowing into the formation, into the aquifer. And that's the opposite of pumping a test, pumping the aquifer. We're basically adding water to the aquifer. But interestingly, we can still use that information by measuring the drawdown after pouring in the water, the drawdown over time. And it's still telling us about the hydraulic parameters inside the aquifer. Such a test we call a slug test. A slug test. We're basically adding a slug of water. I can show you the next slide here. We're adding a slug of water, we're increasing the water level inside the well, and then we're measuring how the water is slowly dispersing and returning to the original water table level. It's the opposite of a pump test. And that's great because these tests are quick, they're fairly inexpensive, but they only information about the well itself, not far beyond the well. Good. So slug tests, they won't, the Darcys method that I explained to you earlier wouldn't work to analyze the test data. For slug tests, you would use a different method. It's called the Darcys method. Darcys method is basically related to the Darcys method, but slightly different. And it's designed for approximating hydraulic conductivity values from slug test data. So this would be an example how a slug test data could be analyzed. So again, we're having time here. And again, this is drawdown. But in this case, we're using a log, and that makes it a straight line. And the slope of the straight line in the Darcys method allows you to calculate the aquifer parameters. Again, I won't go into much more detail. This is something that usually requires an additional class, just focusing on this type of aquifer test evaluation. However, today there are plenty of information either freely available, like this publication by Kuseman and de Ridder, which again, you can download for free from the internet. Just type in the title, Analysis and Evaluation of Pumping Test Data, and you have a full description of how the Darcys method and the Darcys method work and how pump tests are being conducted. Nowadays, there are also very powerful computer programs. One piece of software, it's called Aquifer Test. There's a link here that gets you to the Waterloo Hydrologic. You can actually download a test version of this, a trial version of this software. The same is true for AccuTE Solve. This is a different type of software. You can also download a trial version. And by doing so, you can play with drawdown time data, the Darcys method, the slug test method, and explore how easy it is actually to calculate hydraulic conductivity and so on and so on. There's a free piece of software. It's Aquifer Tests, and it's by the United States Geological Survey. It's a little clumsy relative to the much more slick commercial products, but this one is for free. So it is definitely interesting to just download it and see if you can use it. Good. And that's all I can say in this time we have. And again, I was trying to make it as intuitive as possible, but I totally realized that running a pub test is something you're learning by doing. This is something that you see how it works by going into the field with an experienced hydrogeologist who will tell you what to do. And once you've done it, and with this lecture in mind, you will find it very easy to calculate what are the important hydrologic parameters for your aquifer. And that's how you make your money. That's where customers pay you for, to tell them how much water they can pump from wells, how much irrigation water, how much industrial water they will get. And this is important information. Absolutely important information, and the pump test is the means by which you get this information. So with that, I like to stop and open up the round for questions. I'm sure you have lots of questions because this was not a simple matter. So thank you for your time. And if you have either questions in person or in chat, I will try to answer them. Thank you so much.
Okay, thank you for your presentation, Prof. Bufing. And now we continue to question, please. You can ask question for yesterday lecture maybe, or for this for today. You can ask about this material or in this Zoom class. Okay, please. Who will
bisa tanya pakai bahasa Indonesia juga nggak apa-apa, Pak. Saya kira. Kalau mau nyaman dengan bahasa Indonesia juga mau, silahkan aja.
Boleh pakai bahasa Indonesia.
Bahasa Arab juga boleh. Cina juga boleh. Bahasa Indonesia boleh, nanti ditranslate. Nah, itu ada tuh, Mbak Tiara, Mas Bintang.
Ya, silakan, ada ini yang raise hand. Silakan langsung open mic. Can you open mic and open your camera?
First, I'm sorry, Miss, because my connection just unstable.
Oh, okay,
so
it's okay.
I can open my camera.
Oh yeah, okay, it's okay.
Okay, thank you. Okay, thank you, Miss. Let me introduce myself first. My name is Tiara. Okay, sir. First, I wanna say thank you so much for the materials. I want to ask two questions actually. First, how do we know the depth of the saturated aquifer that will be placed in the pumping well itself? And the second one is the curve that this method always the same as the ground is stable or not, Miss?
Mm-hmm.
Yeah.
Okay. Thank you for your question. The answer to your second question, the Tice curve will remain the same always. And that's the beauty of the method. Once you have plotted the data, the WU versus 1/U, you only do this once in your life. Or you can use the copy of my slide, actually, if you like to. And all you need to do is then use this type curve, and that's why it's called a type curve, to lay over your measured printed drawdown. And you will see it's like a miracle. It always fits. It always fits. And that's all you need to do is to take your type curve and put it on top of your drawdown data. So the first question, could you repeat that? Because it was breaking up when you asked the first question and I had to, can you repeat your first question?
Oh, okay, sir. How do we know the depth of the saturated aquifer that will be placed in the pumping well itself?
Oh, good. Yes. Okay. So how do we know the thickness of the aquifer? Sometimes we know it because we have a fully penetrating well. That means when we drill the well, we will see that eventually, let's say, the geologic material changes from sand and gravel to, let's say, bedrock or some other material. Then we stopped drilling, and then the driller will tell us, oh, we are now at 105 meters when we hit the bedrock. Okay, so you know the depth to the well is 105 meters, and you also know what is above, because during the drilling, the driller will tell you, okay, so we now have sand and gravel. Now it changes to, let's say, clay and silt. Now it changes again. So you have a very detailed drill log. We call it a drill log, where each level in the well has the geologic characteristics associated with it. And sometimes you have like 100 meters of just sand and gravel. That's ideal. So this would be a very fantastic aquifer. And then you have what we call the B value, the thickness of the aquifer, and that's all it is. So yes, what you need is a very detailed drill log that states the depth of the well and the material that is being drilled through. Does that answer your question?
Yes, sir. Thank you so much for the explanation. Thank you.
You're welcome.
Okay, for the next, please, Bintang Ramadan, open your microphone and camera.
Okay. Thank you for the opportunity, but sorry in advance, I cannot turn on the camera due to network problems. Okay, my name is Bintang Ramadan Prakasa from Environmental Engineering, Islamic University of Indonesia. As we know, groundwater has a lot of mineral content due to the infiltration process, which indirectly absorb forms of chemical compound that exist on the soil surface. In the case study, the addition of NPK fertilizer with the aim of fertilizing the plants actually has a negative impact, which will give a score effect and make the plants wither in the quantity of fertilizer which use is excessive. It will indirectly affect the quantity of groundwater around it. My question is, what is your opinion regarding in the case study, and as someone who is close to the environment, what should we do to overcome this? Thank you.
Okay, good question. So you're absolutely right. If there's an influx of excess fertilizer into the groundwater from the surface, right? So let's say a farmer spreads out magnesium sulfate or potassium nitrate, whatever, ammonium sulfate, then with rain, the fertilizer will dissolve and then slowly make its way into the unsaturated zone until it reaches the water table, the groundwater table. What you get is an increase in total dissolved solids, meaning the salt content of the groundwater is increasing, and it can increase to the point where the water is actually tasting salty. And having too much ions like magnesium or sodium or potassium, ammonium in the water makes the water unfit for human consumption, may even be no longer useful for irrigation water. This is a big problem in agricultural areas, and I can give you some examples from India, where we have seen the water in agricultural areas, the groundwater being so salty that people can no longer use it for agriculture, or they cannot use it for drinking, for anything. And this is a big problem because it is very difficult to remove total dissolved solids like sodium or chloride from the groundwater, because usual typical filters do not work for these contaminants. What you need is reverse osmosis or ultrafiltration. But these are very expensive and complex methods that typically cannot be used on a large scale because it's too expensive and too energy intensive. So the best way out of this is to control the amount of fertilizer, meaning minimizing the amount of fertilizer. And that means you have to educate farmers, particularly farmers that are less educated, have a low education. You need to explain that excess fertilizer is harmful, not just for the plants, but also for the water. It's a long-term proposition, and in India, we have tried already for 15 years, and it's a very slow process, but it is best to avoid contamination than to clean it up. That's for sure. I hope that answers your question.
Okay, thank you, sir, for explanation.
Okay, for the next question. Any else? Ada lagi yang ingin ditanyakan?
Ini masih berapa menit, Mbak? Masih
Sekitar 17 menitan lagi.
Teman-teman mahasiswa kalau ada. Kalau nggak ada, saya tambah sedikit tentang barangkali nanti bisa diskusi dengan Pak Tom. Ya, Pak Tom. Halo.
Yep.
Okay.
Oh, hi. Oh, no, I can see you.
To see you again. Okay, let me show you another case. Moment. Can you see the PowerPoint here? Yeah, this is the example of what we call pre-bin underground. Yesterday you mentioned about limestone karst, right? Limestone. Maybe you have been there in here in Gunung Gitu.
Yeah, I've visited the site. I was even down in the.
Oh, and this here. Yeah.
Oh yeah.
Very nice. Yeah. I think you have been here.
Yeah, very impressive. Very impressive.
Yeah. You have been here, right?
Yes.
Yeah. This is very interesting project, I think. There is so many people call this river is also they call aquifer. The people Gua mean cave. Pripin, the name of the cave. So with this cave, it is stalactite.
Yes. And, very beautiful. Yeah.
And this is actually this is a river, right?
Yeah.
It's a river. But so many people also call that it is aquifer, not the river.
Yeah, right.
Yeah. So it is in terms of the term of aquifer or river, almost the same.
Yeah, right.
Almost the same.
So you're right. This is karst is the only time when you really have groundwater rivers, and karst is only covering a small fraction of the surface, right? So most of the times, I would say 90% of the time, you don't have rivers, and flow takes place in either the pores or the fractures and fissures in rocks.
Yeah, you're correct. But the question now is how to conserve what we call catchment area.
Yeah.
It's not clear right now how to conserve the catchment area here in this case of Pripin cave or Pripin River or Pripin Aquifer or whatever we call.
Yeah. No, there's a very common problem in karst. It's very common because we don't really know where the water comes from because it's unpredictable how the limestone is dissolving. These limestone caverns, they typically going back and forth, meandering. It's not a straight line. So it is almost impossible to determine where is the recharge area, how large is the watershed. And in Germany, for example, there's an area of karst near my university town where for 100 years, people have tried to delineating catchment area of one particular karst spring, and they still don't know.
Very expensive, very long. Very long time.
Right. It's called the Blautopf in southern Germany, very famous spring. And they used dye tracer, they used salt tracer many times, and it's still not clear where in the karst area the groundwater is flowing. That's why karst is so interesting and so complicated. There are entire books, books written on the karst.
So, for example, of Gunung Kidul, in this case, the problem is not the water resources itself, but the problem is about the energy. How to pump, how to get the water from the underground to the surface here. It is the problem. How to flow the water up here.
Right. Yeah. Right. That's the question of hydraulic head. So if the hydraulic head is not large enough, you don't force the water. You're not able to force the water up to the surface. And I guess that's really. I guess the only way to do this is to have such an underground dam built at higher elevation, and then instead of getting the water up vertical to the surface, is to have the pipes go down at the slope of the hill. Right? I mean,
This is a dam. This is a dam.
Yeah, exactly.
Yeah, but another problem is the crack of the limestone, the karst here. So leak of the water is kind of leakage.
Oh yeah. Right. That's another. You're right. You have to basically, before you fill the cave, you have to completely seal all the cracks with concrete or some rubber or whatever.
Yeah, but it is big here. Yes, very big here. So complicated, very complicated.
Very difficult, and probably not going to be effective because you get one small earthquake and then you have even more cracks, and then So
this is the example of earthquake. You see,
the
impact of earthquake.
Oh wow!
The rock was like that, and then kind of the block. They block in the water.
Wow!
They block the water. So they did like that. How to say? What we call like bomb. You know what I mean, bomb. So they went to enter in the cave, and then they bring what we call dynamite. I don't know how to say in English.
Dynamite.
Yeah. So and they bomb the dynamite, and then the rock is become smaller and smaller.
Oh yeah.
Yeah. So this one. So they can flow together with the water. It's not blocking the water anymore.
Yeah.
It is very dramatic at the time. It was very dramatic because it takes maybe 8 hours from the mouth of the cave going into the cave to the rock itself. 8 hours, more than 8 hours, I think. They walk inside the cave.
Wow. That's amazing.
You just notice it. At that time, many people, maybe die. There's no news. Already very dark in the night time, you know. Maybe on the plan, maybe just 5 o'clock should be show up. But I think up to 10 o'clock at the night, there is no news about that. No, because no WhatsApp, no SMS, and so on, so on. So
that's a very interesting project. That's a very interesting project. I think there are not very many projects like this on Earth.
Only one.
Only one.
Yeah, the only one. So it is the example and would be replicated in Russia. At that time, will be replicated in Russia.
Oh, I see.
Yeah, Russia.
Yeah, that's amazing. And that's right here. It's only half an hour by bus.
Yeah. It's very cheap from here. Oke, itu tambahnya Mbak Nelly. Barangkali ada yang lain, silakan.
Matur nuwun Pak Widodo. Okay, the last question maybe. There is no question.
Barangkali yang bertanya tentang jam-jam itu sebetulnya rantai-rantai itu kenapa ya? I just speaking in bahasa. What about jam-jam water? Do you know what I mean jam-jam water? Jam-jam. You don't know. Mbak Imam mungkin bisa, Mbak Nelly bisa menjelaskan jam-jam water. Oh, itu ada. Maulana ada tanya itu.
Okay, please, Mr. Maulana.
Yeah, thank you for the opportunity to let me ask a question. Yeah, that question is, I just wanna ask about the Zam-Zam water, and I just wanna ask about that, and I wanna ask you about the pumping Zam-Zam water well in Saudi Arabia. As we know, the Zam-Zam water well is a miracle of the Prophet Ismail, where the water comes out by itself from the ground, and this incident took place for centuries from before centuries, and until now, the well of Zam-Zam water is still used today, and the spring is never run out. So Zam-Zam water is also experiencing an increasing demand for it every year. My question is, do we need to do special treatment regarding the pumping of Zam-Zam water in order to maintain the sustainability of the water resources? How do we preserve the water? Do we need to build a new water pumping installation? That's my question.
Yeah.
Thank you.
That's very interesting. I wish I have had a chance to look at this spring. So what I'm thinking is happening here, we have an artesian well. An artesian well is basically producing water from a confined aquifer. And in a confined aquifer, the water is under pressure, hydrostatic pressure, which forces the water from very deep to the surface. And as long as the flow rate of the well is low, relatively speaking, to the size, relative to the size of the aquifer, then this can go on for centuries, because the water that is coming out of the well is recharged at sometimes far away distance, maybe 10, 20, maybe even 100 kilometers away. The water is recharged and it finds its way in the underground to the discharge point, to the well. So this can go on without any pumping. However, if, let's say, farmers or cities drilling into the same aquifer that supplies the Holy Spring and start to pump water from the same aquifer, they're lowering the hydraulic head in the confined aquifer. And once the hydraulic head is falling beneath the surface of the earth, then the water stops flowing, right? And the only way to reverse this is to either stop pumping or increase the recharge. And increasing the recharge is a problem because we are in Saudi Arabia and it's very dry. So the little rain they get is not sufficient to overcome the amount of water that's being withdrawn by the cities and by the irrigation, by the industry. So if you want to protect the Holy Spring, you need to stop pumping water from the other wells. And then hopefully over some time, the flow of water will resume to normal. So that means what you have to have is a water management strategy. A water management strategy is where all the users of the water come together and decide how much water is safe to pump from the aquifer. It's called a safe yield. And only if people decide to pump the amount of water that's being naturally recharged, only if you not go over that volume of natural recharge, then you can run an aquifer safely for a long time. But that's very difficult because everybody wants a lot of water, right? The industry wants water, the farmers want water. So often what people do, they pump more than they should, and that means the hydraulic pressure in the aquifer goes down, and all of a sudden the well stops pumping. So yes, confined aquifer, probably a very large aquifer, and that would be my best guess. Like I said, I've not had the chance to visit the area, and I hope that people can protect their well from going dry. Does that answer your question?
Yeah, yes. Thank you for your answer. Thanks for your explanation, sir.
Okay. I think that is the last question. And before we end this class, we can take picture together. Please open your camera.
Always taking picture.
Yes.
Please open your camera.
Open our camera. Come
we
on.
will still waiting you for open your camera because we will take picture together.
Gimana motretnya gimana? Sudah ya.
Oke.
Oh, hebat.
Mbak Ratna or Mas Heri?
Ini berapa? 156. Wah, ini 5 kelas ya.
Oke, kasih aba-aba ya, Mbak.
Ya, untuk slide 1 ya. Oke. 1 and 2 and oke.
Ini
Slide 2. Oh, ini nggak pada buka kamera.
siapa?
Silakan open your kamera.
Slide 2.
Wah, ini kosong.
1 and 2, 3.
Ini Puja Putri malah nangis ini.
Itu adiknya Mbak Puja itu, Pak.
Oh, gitu. Ada Muhammad Afif Einstein itu.
Ini Mas Husni itu Mas gambar kamera ini, Pak. Lihat. Oke. Satu lagi. Sip. Oke, Mbak, sambung.
We can give applause virtual for Prof. Bufing.
Ya.
Or
Gimana gambarnya virtual applause gimana ini ya? Klap gitu ya.
Okay. Thank you very much for Prof. Bufing, and I hope we can meet again another
Nice
time.
meeting you, everybody. Nice meeting you, everybody. Good luck with your studies.
Okay, I mean, yes. Okay, we will end this class. Thank you for your attention and see you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
warahmatullahi wabarakatuh. Pak Tom, buat tonight, buat wah sorry. Sudah maaf. Sudah. Yes, for tonight, what time are you ready? About 6:30 or 7 o'clock?
7.
All right, yes, 7 o'clock. The driver is going to pick you up. Oh, I think it's already with you right now in campus.
Yeah.
Should be checked in first.
All right, yes, okay.
At
All
hotel.
right. So
I mean, we can also go first and then check in. Maybe that's better for you. Otherwise,
better for you. Up to you. For me, it's no problem. You can 6:30. You can when it says 7 o'clock.
6:30. 6:30. Okay. Yeah.
6:30.
Everybody says it's okay.
All right. Yeah. Okay. I'll see you over there.
Okay. Wonderful.
Thank you very much. Yeah. Okay. Terima kasih, Mbak.
Okay. I'll see you at.
Siap. 6:30 sayang. Atur nuhun. Assalamualaikum.
Waalaikumsalam.